All right, recording is rolling on Wednesday, October 7th, and let's take a look at this model. You guys know last 2 days we've been doing centripetal force and universal gravitation. We've been putting those ideas together to start talking about orbits. Okay, so let's go back about 1,000 years ago and think, what did people think the solar system looked like about 1,000 years ago? And this was the model that they had. This is called a geocentric model. You get geocentric, like Earth-centered. That's the Earth at the center and everything going around the Earth, including the sun. You guys see the sun going around? Okay. Sometimes it's also called a Ptolemaic model because after the Greek thinker Ptolemy. But well, let this run long enough, and you see some problems with it. And that's that. See how these planets have this like spiral type pattern? They look like they're kind of moving kind of backwards in the sky at some point. I mean, if you keep really close track of the planets, then from Earth's point of view, that seems to be what's going on. You guys know the word planet is a Greek word that literally means wanderer, like wanderer, right? So those planets would be wandering in the sky relative to the background stars. From Earth's point of view, it looks like everything's going around us. But then also sometimes they kind of wander backwards. That's weird. I wonder what would cause that. So this is the model people were using for a long, long time in history. No one had a good explanation for why the spiral pattern would be there, but it seemed to check out and work. I guess you could describe the solar system that way. But then along comes a guy named Copernicus, and he says, well, hold on a minute. I can rearrange this and create a much simpler model. I can, if you put the sun at the center, have a sun-centered model. This is called a heliocentric model, also called a Copernican model of the solar system. Then actually that's a much simpler model. Kind of like Occam's razor, the simplest answer is usually the correct one, and that's this case too. So he says, actually, the Earth is revolving around the sun, which was counterintuitive to people at the time because it feels like we're not moving. But you guys know that that's okay, that checks out because all motion, all velocities are relative anyway. So of course you don't feel the Earth like flying through space because, well, you don't feel the velocity of Earth. Velocities are all relative. Actually, it was illegal at the time to think things like this. And Copernicus actually published this idea in a book the very day that he died, like on his deathbed. His book was published that said this. You guys know that Galileo was actually under house arrest for the last few years of his life for actually espousing this same idea, this heliocentric model. But this greatly simplifies the solar system, doesn't it? Because now you got this just everything's in those circular type orbits. Now, we can talk about that too. Not exactly right, but and you don't have to explain all that spiral pattern, which what would even explain this. Okay. So after Copernicus, but before Isaac Newton, comes along this guy named Johannes Kepler, and Johannes Kepler was looking at a lot of data collected over many years by a guy named Tycho Brahe, and he was trying to get exactly what these orbits were because he was onto this idea that, well, hold on a minute. Maybe these orbits aren't exactly circular. Maybe they're pretty close to circles, but maybe not exactly circles. Now, you guys might remember from last couple of days that a circular orbit is actually a very fragile system. Like if you went like a smidge slower, you eventually like spiral and crash into whatever you're orbiting. And Kepler was onto this idea. So we have Carl Sagan explain Kepler's laws of planetary motion.
Tycho had told Kepler that the apparent motion of Mars.
Yeah, there's the apparent motion of Mars from the point of view of Earth. Yeah, what causes this retrograde motion? Well, now you guys know it's all relative motion of the planets.
Was the most difficult to reconcile with a circular orbit. After years of calculation, he believed that he had found the correct values for a Martian circular orbit, which matched 10 of Tycho Brahe's observations within 2 minutes of arc. Now, there are 60 minutes of arc in an angular degree, and of course, 90 degrees from horizon to zenith. So a few minutes of arc is a very small quantity to measure, especially without a telescope. But Kepler's ecstasy of discovery soon crumbled into gloom because 2 further observations by Tycho were inconsistent with his orbit by as much as 8 minutes of arc. Kepler wrote, "If I had believed that we could ignore these 8 minutes, I would have patched up my hypothesis accordingly. But since it was not permissible to ignore them, those 8 minutes pointed the road to a complete reformation of astronomy." The difference between a circular orbit and the true orbit of Mars could be distinguished only by precise measurement and by a courageous acceptance of the facts. Kepler was profoundly annoyed at having to abandon a circular orbit. It shook his faith in God as the maker of a perfect celestial geometry. Having cleaned the stable of astronomy of circles and spirals, he said, he was left with only a single cartful of dung. He tried various oval-like curves, calculated away, made some arithmetical mistakes, which caused him, in fact, to reject the correct answer. And months later, in some desperation, tried the formula for the first time for an ellipse. The ellipse matched the observations of Tycho beautifully. In such an orbit, the sun is not at the center, but is offset. It's at one focus of the ellipse. When a given planet is at the far point in its orbit from the sun, it goes more slowly. As it approaches the near point, it speeds up. Such motion is why we describe the planets as forever falling towards the sun, but never reaching it. Kepler's first law of planetary motion is simply this: a planet moves in an ellipse with the sun at one focus. As the planet moves along its orbit, it sweeps out, in a given period of time, an imaginary wedge-shaped area. When the planet is far from the sun, the area is long and thin. When the planet is close to the sun, the area is short and squat. Although the shapes of these wedges are different, Kepler found that their areas are exactly the same.
And what he just told you right there is actually this Kepler's second law of planetary motion. So because the shape is elliptical, sometimes the planet's further away, sometimes it's closer to the sun. That's the first law of planetary motion that Kepler got just from looking at this data, just this very precise data. The sun is at one focal point of that ellipse. And when the planet's a little bit closer, it swings by a little bit faster. And vice versa, when it's further away, it goes a little bit slower. A really good explanation of that comes from conservation of energy that you guys haven't learned yet, but hopefully it's somewhat intuitive, maybe. But the size of these wedges is the same for equal time. So equal times, equal areas. Say it takes the planet 30 days to go from here to here, and 30 days from here to here. Those wedges are the same size. Now, it's one reason it's really amazing that Kepler was able to figure that out is because I think it's a kind of an integral calculus type thought process. I mean, if you're trying to figure out some area, some weird shape. Remember, this is all before Isaac Newton even comes along. And with Newton, you get calculus and physics and all that stuff, right? So first of all, planetary motion, planets actually move in elliptical orbits, which probably kind of makes sense based on, remember yesterday, you guys remember Newton's cannon, you can get a circular orbit with exactly the speed, but that's really fragile when you slowly spiral down and crash. So ideally you want a little faster than this, which actually would put you to elliptical orbit. If you go faster, you get an even more elongated orbit. Eventually you might reach escape speed, but hang tight there. It's not quite ready for that yet. So second law of planetary motion is the equal size wedges for equal times rule. The third law of planetary motion, Kepler was able to figure out many years later, and it relates to the time period of a planet around the star to its average distance from that star. So all planets within a solar system, some orbiting some star of some given mass, the square of their time periods are directly proportional to the cube of their distance from their parent star. Now, once you incorporate Isaac Newton universal gravitation, you can actually come up with a modern version of Kepler's third law, which is this right here. It says that the time period for a planet to go around, so for Earth, this would be 365 days, is equal to this expression right here. The average distance from the star, universal gravity constant, mass of the sun. Okay, you just pop in there. So it's an updated version of what Kepler figured about that proportionality. Okay? Guys good so far? You guys should have a red string. Tie that red string into a loop. And some of you guys already have a loop from last class. Does anybody not have a red string or loop? Does anybody not have that?
My string is like fully knotted. It has
Oh, okay. Yeah, let me get you a new string then. Okay, so while you guys are tying that, so just tie a loop. Okay. Actually, I have a couple from earlier, so if you want to be.
Yeah, mine has 3 as well.
Oh, okay. Who else needs that? All right. Got 2 more.
What?
Couple of strings for guys.
Everyone's time is
Yeah. Yeah, just like a loop. Oh, okay, yeah, that's good. That's what you want. Right, who else needs a string? Yeah, not really. That's a new loop. Okay, who else?
I didn't do it. That's fine.
Yeah, sure. Who else? Oh, good. Right, anybody else? Who else needs red string? Good. All right, now you guys got a loop of string.
There we go.
I'm gonna do this with 3 pens. One to actually draw with, and the other 2 to keep some markers. So go throw down a couple marks right there, and take a pen. And you guys see that triangle shape right there? See a triangle? Okay. So I'm gonna keep these bottom 2 pens in place, and take this dark blue color, and go all the way around. Now that string is always keeping some kind of triangle shape, and it's constraining the motion of this curve. So it looks like that. Hey guys, what shape does that make? What shape is that?
Circle.
It's not a circle exactly.
Oh.
It's an ellipse. It is an ellipse. Yes. Look, actually, it would be a circle if what? If these 2 points were, yeah, the same. If these 2 points were on top of each other. So actually, a circle is a special case of an ellipse, just like a square is a special case of a rectangle. Okay, like that. Okay. And if you guys paid real close attention to Carl Sagan telling you guys, do you guys catch that for Carl Sagan or for Kepler to figure out that the path of these planets was elliptical? Remember, he's looking at a bunch of data that was so the motion of the planet Mars, where exactly was Mars positioned in the sky? Okay. The difference between the true elliptical motion of the planet Mars and what would be a circular orbit was, well, if you guys know what 1 degree is, right? You guys work with this protractor. You guys know 1 degree is like 1 little tick mark. Right? So if you divide 1 degree into 60 units, each of those is called a minute. So 60 minutes in 1 degree. The position of the planet Mars in the sky was off by 8 minutes from a pure circular path. So that's how Kepler figured out that, ooh, it's actually not going to be a circle, right? Which is like really close to, but it's not exactly right. And this, of course, is the path that a planet would follow around a star. So it's like a planet, and the sun would be at one focal point. Okay. Now, at a glance, like if you weren't paying real close attention, you might say, "Oh, that's pretty close to a circle." But these focal points, oh, and that's what these are. These are focal points. I call those foci. Are pretty far away from each other. If I brought them close together, that might be more realistic to like the Earth going around the sun. The Earth going around the sun, I mean, it's definitely more of a circle than what I have on my page. But you see how far away those are from each other. Okay. This will actually be maybe closer to a comet shape. You guys know comets have highly elliptical orbits. Like they're ellipses, just really stretch out. Okay. So this is the shape that a planet falls around the sun. I want to talk about the geometry of an ellipse because there's actually an interesting mystery about ellipses that I'll introduce you guys to. So suppose you make this axis that goes through both focal points. Okay. And I'm going to make some axis arms that just go straight to the center. So at the center, go 90 degrees and go this way. Okay. And those axis arms I'm going to call A and B. So got side A and side B. Is it side A and B? Okay. And maybe I'm interested in some properties about this ellipse, like maybe the area of the ellipse and maybe the perimeter of the ellipse, something like that. And I know some values for circles, because what's the area of a circle equal to? Pi r squared? Yeah, pi r squared, right? Okay, what is the circumference of a circle equal to? 2 pi r, right? That be true? Okay. If you ever mix those up, by the way, because a lot of students do, remember that r squared, that's like getting like square inches, square feet, square meters. That would refer to an area. Okay. Versus a linear distance, like inches, feet, or meters. Well, you could measure a circumference like that, couldn't you? Like some linear distance. Okay. So what's linear and what's square? Okay, so we know that. I wonder what the area of an ellipse would be. Like this ellipse right here. What do you think that area is? And if you know what it is for a circle, which is pi r squared, and you're looking at this geometry, like A and B, I bet you guys can figure it out. What do you think the area of that ellipse is in terms of A and B? How about this? If this were a circle, wouldn't A be equal to B, which would just be R? And wouldn't the area of that then circle be pi times R times R? That's what pi r squared is, right? Ah, so for an ellipse, it must be what? Pi times A times B? That's it, pi AB. Right? So if you took A and B, let's say you made a rectangle, A times B would be the area of this rectangle, you guys see that? And then you multiply that by 3.14, you pretty much well get the area of that ellipse. All right, one more question. What is the perimeter of this ellipse? That's to say, well, since this is a physics class and we're talking about the distance that a planet goes, how far does the Earth exactly go around the sun in 1 year? That would be the perimeter of an ellipse, wouldn't it? Does anybody know the perimeter of this ellipse? I'm going to say you don't. And I'm going to say that because nobody knows. This is one of the mysteries that no mathematician has ever exactly unlocked. Now, there are approximations. There are some formulas that get pretty close, but nobody's figured out exactly what the perimeter of an ellipse is. Nobody knows. So that's a mystery. Maybe one day, one of you will master in math and figure that out. So we're looking at these elliptical shapes. Let me go back to the story of these formulas and add on to the story. Okay. So you guys know now that a circular orbit you can achieve with this speed, but that'd be a fragile orbit. Realistically, you want to speed this up a little bit, and that's what you actually observe in nature. That's what Kepler figured out, is that planets actually follow elliptical shapes. Same thing with asteroids, they follow elliptical patterns, which is a little bit faster than this, going around the sun. But if you speed it up even more, you get comet orbits, which are also ellipses, but they're highly elliptical, right? So very elongated. Right? Actually, you guys remember the very first day you ever walked in this class? I had a PowerPoint. I was telling you guys the story of Halley's Comet. And so back in the 17th century, bunch of astronomers were trying to figure out what's the shape of this path. And then went talked to Isaac Newton, and then since we have to talk about some physics. Okay. But if you get going even faster, you might eventually hit escape speed, and then you could just escape the gravity of whatever you might otherwise be orbiting. Right? So what if something flew by the Earth? Let's say a little tiny asteroid flies by Earth, and it's pretty close, so Earth's gravity bends its orbit, but it's going way too fast. It's going faster than, say, this expression. So it's going to fly away from Earth. It's not going to loop back on itself. That would be an ellipse. So it's going too fast for that. It's going to fly away. Okay. What shape is that called? It's called what? Starts with an H. Hyperbola. That would be a hyperbola, right? If you're going faster than escape speed and you go past a gravitational body, you'll actually take the shape of, like a hyperbola. Right? The reason I want to bring that up is because I want to tell you guys a fun side story here. Fun side story time. So you guys know that astronomers are keeping track of like thousands of asteroids in our solar system, right? Like, especially the ones that might possibly hit Earth. Like, you definitely want to keep track of those. I can tell you one of the big news stories of the year 2029. So what's going to close out this fun decade is there's going to be a really close asteroid flyby that's just barely going to miss us. So that will be a news story one day. And look at a picture of our solar system. Let's get the sun. Let's get the Earth. Let's get some sort of a side view. So look at kind of from the side. Here's the Earth going around the sun. And thousands of asteroids out there. They're all kind of spherical in shape. They all follow elliptical paths, just like the planets do. You get some comets every once in a while that follow these highly elliptical paths, like comets. And then in 2017, there were some astronomers over at an observatory in Hawaii. And they were looking up, okay, they see something new in the sky. Hey, we've never seen that before. Well, let's make a note. Let's track its path, see where it's going. And after a while, when they got enough data, they were able to track its path. They're like, oh, we realized we're seeing something that we've never seen before. This path is not an ellipse. This path is a hyperbola. This is a hyperbolic path. Which means what? What does that mean? The fact that it's hyperbola. This object came from where? Came from outside our solar system. Came from interstellar space. that's the first time we've confirmed that that there's been something that's passed pretty close to us that is actually from interstellar space. Yeah, it passed right through our solar system. Okay? Well, the hyperbolic path. Where did it come from? Well, that's an open question. That's a mystery. Nobody knows. Okay? This object has a name. Actually, I bet some of you guys know this because this was a pretty big story. Does anybody know what this object was called? It's a Hawaiian name. Oumuamua. And if you Google Oumuamua, well, there's no really clear picture of it, but there are some artist renditions. And those artist renditions are actually based on, well, some other weird property of this object. So remember how I told you guys that pretty much every object that we see floating around in space is kind of spherical or spherical-ish? Like the planets are spherical, asteroids are pretty spherical. Right? If you look at the light coming from this Oumuamua object, I'll say light as a function of time, like what's its light curve look like? It actually looks like this. It gets bright, dim, bright, dim, bright, dim, which is pretty strong evidence that it actually probably is not spherical. Yikes, that's another weird thing about this. So not only is this the first and only object that's interstellar that's passed by us as far as we know, also it's probably not even spherical. So a lot of the artist renditions draw it like a log shape. That could explain this curve because maybe it's tumbling through space and sometimes it's spaced like this towards Earth and sometimes it's this, so it's like bright, dim, bright, dim, bright, dim. It could be something like that. Nobody knows for sure. Right? There's another proposal that, well, maybe it's actually like a big flat sheet. Maybe like that could also, as it's tumbling through space, produce a similar type curve. Like, that's possible. Nobody knows. It's probably something in that ballpark. Okay? But you know what? There's actually a third weird thing about this object that I haven't told you guys yet. Okay, so first weird thing is from interstellar space following this hyperbolic path, only one that we know of. Second weird thing is that it's probably not spherical. It's doing this weird thing. The third weird thing is that actually it didn't even follow exactly the path that it was supposed to. So you can use Einstein general relativity, which is like an updated version of the Newtonian mechanics you're learning in class, to pinpoint exactly where an object is supposed to be, like its exact path. And this thing leaving the solar system actually took a path that it wasn't supposed to, according to Einstein's theory of relativity, which has been really successful in predicting like pretty much everything that's macroscopic. But this actually broke that. So now there's open speculation as to what would cause that. There are different hypotheses, but nobody knows exactly why. One popular hypothesis is, well, maybe this thing is kind of like an icy ball, kind of like a comet. Maybe it's outgassing an invisible gas that we can't see, like nitrogen. That's possible. Or maybe if you like the idea that it might be like a flat sheet of something, maybe there's some solar wind that's pushing it. Like that could possibly explain it. But again, it's an open question. Nobody really knows. So yeah, I'm thinking about that one. One more fun thing I want to show you guys. Flip back over the present screen too. Okay. Let me tell you guys about Lagrangian points. You guys know a mathematician named Euler? You guys know the E number, E button on your calculator, like 2.718 number, like named after Euler? Euler's formula. Euler probably did more mathematics than anybody else. A lot of mathematical properties that are named after other mathematicians, Euler actually discovered first. He just discovered too much stuff, so can't name everything after him. But one of the things that Euler laid down the math for was the first three of 5 Lagrange points. You see them here, L1, L2, L3. Now, what are these about? These are points of gravitational stability. Could you guys imagine there's probably some point between the sun and Earth where gravity kind of cancels out? Like the sun pulling left and the Earth pulling right could balance out like that. Okay, so that could be an L1 point. Now, that point is not super stable. Yeah, you could park a space probe out there, but it's kind of like trying to balance a ball on top of a roof. If it gets bumped a little bit way, it's just going to tend towards that way. Going to roll away, right? Now, what about L2? Now, you can make sense of this one too, because there's some point at L2 where the sun is pulling you to the left, the Earth is pulling you to the left, but because of rotational dynamics, you might be along for the ride, like in an orbit that matches Earth, where you can look down beneath you and you see the Earth like beneath your feet, but you never actually fall anywhere closer towards it because of this rotational effect. So as you're revolving around the sun with the Earth, you never get any closer. That'd be like an L2 point. Well, if L2 exists, you can do some logic and figure that L3 must also exist. And these are the three that Euler laid down the math for. Right. There actually is a point of gravitational stability at opposite of the Earth, on the opposite side of the sun. You guys know that we never sent anything into space. Well, humanity never sent anything into space until 1957. You guys know that? So before 1957, there is some speculation, actually good reason, to think that there might actually be like a mirror Earth out here, like some dark Earth at L3. No, we've looked at there in the meantime. There's nothing really out there, but good sci-fi stories. Okay, so those are the first three. Now, after Euler comes along a guy named Lagrange, who these points are actually named after. And Lagrange did a lot of work with physics from the point of view of energy and energy conservation, which we haven't talked about quite yet in class, but we're getting there. And he did some really fancy math to show that, actually there's two more points of stability that Euler had overlooked, and that's L4 and L5. You guys see some equilateral triangles that looks like an equilateral triangle each way, right? So if you make these equilateral triangles, you can actually show that if you have a rotating frame of reference, L4 and L5 are also points of gravitational equilibrium. And I want to show you guys an animation that shows this to be true. Here's the animation. So here's our solar system from above, got the sun in the middle, the inner planets. Here's Jupiter out here going real slow. Actually, the speeds of those planets could exactly relate to each other by Kepler's third law of planetary motion that I showed you guys a little bit earlier. Okay? But let's look at those colored dots. I see some pink dots and some green dots. Those pink dots are the asteroids of the asteroid belt. And notice how it's kind of triangular-ish. Guess that? Kind of a triangular sort of asteroid belt. Okay? Because you guys know the sun is the dominant mass in our solar system. It's like 99% mass of the solar system. But what's the second biggest mass? By far, it's Jupiter. Yeah. So between the sun and Jupiter, those drive the geometry and mechanics of the solar system. And this going back to this pink asteroid belt, you guys see that one of the corners of this triangle-ish looking shape is exactly at the L3 point between the sun and Jupiter. Hey, well, opposite side of the sun from Jupiter, but that's the L3 point. Guess that? Okay. And then what about these green patches? These green patches of asteroids also have names. Those are called the Trojan and the Greek asteroids. The Trojan and the Greek asteroids. I forget if I mentioned before, but you definitely see now that the L4 and L5 points are actually the most stable of all the Lagrangian points. Okay? So if you were to park a space probe at one of those points, L4 or L5, let's say like a big planet swoops by and knocks it a little bit out of orbit, that's okay because it'll kind of gravitate back into place. And that's exactly what these Trojan and Greek asteroids are doing. You guys have probably read Iliad and the Odyssey. You remember the wooden horse, that whole story? Yeah, that's them. That's the Trojans and the Greeks. So there you go. There are Lagrangian points. Okay. So we pick up a story from yesterday where I left off the notes. I just remember yesterday we went on a field trip out in the galaxy. We were exploring and we found this weird planet that was actually a hollow eggshell. You guys remember that? Okay. So recap the story real fast. You can walk around on the outside. It's a perfectly normal planet. Now, maybe you'd be really light because this planet is just an eggshell. It doesn't have very much mass itself, but you can walk around on the outside. I'll find it good. You dig a tunnel, and once you hop inside this eggshell of a planet, it's a completely gravity-free zone on the inside. I showed that for this specific point, but that's really true for any point on the inside. It's a gravity-free zone. Okay? So that's interesting. If you're walking around on the outside, the mass of the planet counts. You can treat it as if it's a point in the middle. GMM over R squared to get your weight. But once you're on the inside, it looks like anything above you in elevation is just going to cancel out, right? Because this is a single shell, but you can imagine I could just do multiple shells. And what we're about to take the story is we're going to tunnel down into a solid planet. You guys ready to go inside a solid planet? And what I want to know is, what is your weight in the vicinity of a solid planet? So let's get a planet going. Have a guy with a hard hat and a shovel. And this guy's gonna dig a spiral staircase all the way down to the center. And maybe brought along with them like a bathroom scale, maybe standing on it right there at the surface. And he's measuring his weight at different places. It's eventually gonna dig all the way down to the center, where maybe he's gonna find a cave. Ooh, a cave at the center of the planet. let's pretend that's not molten down there. Maybe it's just like dirt all the way through. We're going to make some simplifying assumptions like we normally do in this class. So things like uniform density all the way through. Okay? Now, this planet, of course, has some mass. This guy, big M, this guy has some mass, little m. The planet has fixed radial size, capital R. Okay? And since I'm interested in different locations, and what's its weight, different locations, I will call little r a variable radial distance from the center. So the center of the planet is 0.0. Okay? And we're going to put a graph together. We're going to construct a graph. What is your weight as a function of some radial distance from the center? So you could be at the center would be 0.0. Maybe this is measured in meters. Maybe your weight is measured in newtons, something like that. The smallest weight you could have would be 0 weight. Maybe if you get very far away from the planet, it would approach that number. And there's a very special location you could be at, which would be at the surface. So I will label that capital R. You guys good so far? Actually, you guys know what this guy's weight at the surface is going to be, because that's our entire life experience. We've been locked at the surface of a planet. That weight is, well, I might say mg, but the more general way to say it is gmm over capital R squared. Isn't that exactly the weight right at the surface? So it would be right here. So at the surface, he has this weight. If you wanted to call that mg, like lowercase g, remember this lowercase g is only true at the surface itself, so I'll get it, all works, right? Let me just backwards how I've been teaching this earlier today. Okay. Instead of tunneling first, we'll save that part of the story. Let's hop in a rocket and take off in a rocket. Okay. So this little guy, give him a little astronaut helmet. Okay. As this guy gets further and further away from the planet, what's happening to the gravity pull from the planet? It's getting less and less, right? If he gets very, very, very far away from the planet, what value does his weight approach? Yeah, 0, right? So maybe on this graph, I should put a horizontal asymptote at 0 newtons and say, well, if it gets far enough away, then the gravity pull from the planet is eventually going to approach 0. And starting from the surface, can you guys draw that part of the graph? If you're in the rocket getting further and further away, what happens to the gravity pull from Earth? Right? Did you guys draw, I want to see if you guys can beat me to the answer. Did you guys draw a curve that looks like this? Like that? Yep. Hey, does that look like an inverse square relationship? In fact, you know what the equation of that graph is? It's gmm over r squared, right? Where the lowercase r is the variable, kind of like x, right? Is it? That's exactly what it is. This force is proportional to 1 over the distance squared, right? For that part of the curve. Right. Now you guys ready to tunnel down into the spiral staircase journey to the center of the planet? You guys ready for that? Let's go right to the center. I wonder what your weight would be at the center. Let me narrow it down to 2 options, and I want to see show of hands what you guys are thinking. At the center of the planet, you either weigh a lot less than or a lot more than your weight at the surface. So show of hands what you guys are thinking. How many guys think that at the center of the planet, and I'm not talking about pressure, I'm not talking about like there's an ocean of water pushing on you. No. I don't care about that. I just care about gravity forces, right? So gravitational pull, right? Say you were to stand on a scale and get your weight. That's what I'm talking about. How many guys think that at the center, you would weigh a lot less than at the surface? A lot less. Yeah? There's my winners right there. Yeah, you guys are right. Actually, not only would you weigh a lot less, you would weigh exactly how much right at the center? 0. At the center, at 0 meters, you would weigh 0 newtons. Ooh, why would that be? Well, think of it this way. At the surface, the planet's pulling you down. If you navigate, your weight equals gmm over r squared at the surface, then you're assuming that the entire mass of the planet is at the center, but grain by grain, you guys know the mass of the planet is actually spread out over its entire volume. And grain by grain of sand, some of it's pulling you this way, some this way, some this way, this way, this way. But you guys see all the left to right is going to cancel out. But all the down stuff adds up, doesn't it? So, okay, so you're held by a downward force. Okay, so the downward vector is the resultant of all those individual vectors. But once you're at the center, put this guy right here at the center, give him a little hard hat. It's into being pulled this way, this way, this way, this way, this way. Hey, does it look like every single grain of sand on this planet is going to pull them in a different direction and it's all going to cancel out? Right? Yeah, that's what happened, doesn't it? Right? In fact, remember I said this guy has a scale and he's taking the bathroom scale with him all the way down to the bottom? Okay. What floor would he even put it on down at the center? Like, which way is even down at the center? Right? There is no down when you get. This guy would be floating around like an astronaut, wouldn't he? Guess that? Okay, so we've got this point and this point, and also this curve, take off in a rocket. But I wonder how these 2 points connect. Say, like, if this guy's climbing down the spiral staircase, what if he gets like, halfway down? Right? He stands on his bathroom scale there. I mean, he could stand on a scale. Right? Huh. I wonder what his weight's going to be. How do these 2 points connect? Okay. Well, let's think about this. You know what I remember? I remember from the end of yesterday that for the eggshell planet, if you're inside an eggshell planet, that it's as if there's no mass anywhere in your vicinity at all. Let's say anything above you in elevation is going to cancel out. So this guy who's like halfway down inside this planet, okay, if I make a like a dashed line, like a dashed curve, say at this particular elevation, couldn't you guys say that this, say like the crust of the planet is kind of like an eggshell, and then one layer down beneath that looks like an eggshell, right? And isn't there like a series of concentric eggshells all the way down to where this guy is? And would they each individually zero out, right? Zero out the gravity? So it's almost like none of this stuff above him in elevation even exists. And only everything below him in elevation along this dashed path actually pulls him down. Guys, yeah? Great. Now, that'd be a lot less mass than the original mass of the planet, but it's also, he's getting closer to the center, so sort of a trade-off. Let me throw a proposal out here and see what you guys think about this. How many of you guys think that if he's halfway down to the center, he's also going to have exactly half of his weight from the surface? If he's halfway down and has half his weight. How many of you guys think that? Yep, you guys are absolutely right. Now, this I'm not going to preach to you guys today. I don't know, maybe one day, maybe, I don't know. But if you have a planet of uniform density all the way through, then this would be the case. It would be, it'd be proportional all the way down to the center. Okay. Guys, good there? Any questions so far? All right, so we're going to end class with, because that's the main story I have for you guys. So the next thing I got lined up are some textbook problems, but we'll save those for another day. I'm going to switch my screen over and finish class with a video called Spinning. This is a Vsauce video from